For equilibrium problems, let's say we have Cl minus plus O and a mean. Alright, so how we draw the arrows, so which one of these is going to be the base, which one's going to be the acid? Cl minus is going to be the base. Why is Cl minus the base? Because bases are electron dense. Where on the amine, this primary amine, is it electron deficient? There's no H plus on the H. Right, so we take our arrow, start it here. Right, arrows start at electron density. They attack the H. The 2 electrons in this NH bond then go to the nitrogen, right? So we make HCl. And what else do we make? We made the amine. And does it have does it have a charge? Well, what was my overall charge on the left hand side? Negative. Right. The overall charge of everything. Of everything it was right? Here's a negative and here's neutral, right? So overall, what was the whole charge on this side? -1. So what's it have to be over here then? Has to be -1 still, right? You can't lose charge. Right? Who got the electrons? Right? Who got the electrons? This nitrogen did, right? See these 2 electrons here are leaving and going to the nitrogen. And so nitrogen got more electrons. So now the question is, so we've done our arrows. We said this was a base because it's electron dense. We said this then has to be an acid. Now the question that Mac had was, what side are we going to favor? Are we going to favor starting materials or products in this case? And why?
HCl is a strong acid, right?
Yes.
So Cl minus is a weak base.
Yes.
So it should
It should which way? What does strong acids do?
They dissociate.
They react, right? So it should favor
The reactant.
the reactants. Now, if you just say strong acid, that's not going to be a good enough answer. Right? Because you could just memorize the strong acids. Why? The question is, why would it favor? It's right, it does favor reactants, but why does it favor the reactants? So you could say HCl is a weak bond, and that's reactive. But that's different than saying it's a strong acid. Right? So make sure you say it clearly. Right? So remember, reactions only take place for 1 or 2 reasons. What are the 2 reasons reactions take place? One reason, weak bonds in the reactants, or starting materials, whatever they are, or stable products. So in this case, we're already identifying that this HCl bond is weak, right? It's a weak bond, poor orbital overlap. Can we say anything about the stability of the products? Is this Cl minus happy with a negative charge?
Happier than nitrogen.
Right, Cl minus is happier with a negative charge than a nitrogen with a negative charge, and why is that? Cl is more electronegative, and it's bigger. Right? So both those reasons are why this reaction would favor starting materials or reactants.
So because Cl is bigger and is more electronegative than H, it has a little affinity for the H.
That's right.
So you just want to get rid of it.
Just get rid of it. It's reactive. Yes. So if I'm going to redraw these arrows, I would say the arrow would go much more that way and very small this way. So let's do an axial equatorial problem. So we'll do our cyclohexane ring. And what do we want to have on our ring? Pick something. Bromine. You want to go up or down? Down. Good. So now our job is to draw this bromine in a cyclohexane ring in a chair conformation. Right? Now the trick with this is, right, this bromine can be both, it could be either axial or equatorial depending on how we draw the chair. Right? Everybody believe that? So remember how we draw the chairs? We draw 2 parallel lines to each other. And 2 more parallel lines to each other. Then we connect. Right? So the way I like to think of it is this bromine is going back into the board, right? It's away from us, right? I feel like it's it's on the bottom side of the ring. I feel like this is the bottom side of the ring here. So I'll draw here my equatorial, which would be on the bottom side pointing down. I'll draw the bromine in. And the axial position will be a hydrogen, right? So one of the problems I know they asked you guys was to draw in the H's on these centers. Right, so even though the H isn't drawn in, the H is obviously going up, right? It has to be. If the bromine is going down here, the H has to be wedged and going up. Okay? So now we have one type of conformation of the cyclohexane ring with bromine, right? There's just one type. So how do we get the other type? What do we need to do? We flip it, right? We do a ring flip. So how do we do a ring flip? So we just draw a ring, but we draw the other conformation way, right? The way to think about doing it is we take this head of the chair and we pull it down. We take the head and we pull it down. We take the footrest and pull it up to be the new headrest. Right? But to draw these, again, two parallel lines, two more parallel lines, and then we connect the dots. Right? So if I label this carbon 1, where's carbon 1 at in this new ring? Bottom right, right? It's the new footrest. This is carbon 1. Right? Good. It's carbon 1. Yes. And the bromine, did any bonds get broken when we did this ring flip? No. So is the bromine still going to be on the same side of the ring? It still has to be down, right? The problem is now, is this bromine going to be down? If I draw in the bonds for this position, is the bromine axial or equatorial now?
Axial.
It has to be axial, right? Because it has to be on the bottom part of the ring. All right, so that's how we do a ring flip. Yep. So you did a ring flip. We have two different conformations, right? So these are two conformations of this over here, right? There's two different conformations, right? So it's almost like something is like just like cyclobutane can be staggered in eclipse and has those 6 different conformations. 6-member rings have 2 different conformations in this case. The question then is which conformation is more energetically favorable? Something being equatorial, the bromine being equatorial, or the bromine being axial? Equatorial is always going to be more favored. You want to get the big groups equatorial because it sticks out away from the ring. Because you got to remember, in the ring, we don't draw them in, but there's all these hydrogens, right, that are axial to the bromine, right? That's that 1,3 diaxial interaction. Or when you're axial, you're closer to these other axial positions, and again, right, things start bumping into each other, and that's bad. When you're equatorial, you're kind of sticking out from the ring, you're not as likely to run into somebody else. It makes you more stable. So in this case, the more stable conformer would be this. And then you can imagine, right, what if I had 2 groups and I had to choose which one would be axial or equatorial? How are we going to choose? What's the most important thing? What's the thing we don't want to be axial? Big things or small things?
Big things.
Right, big things. So if you look at if you had chlorine versus bromine, which one would you rather have be axial? Chlorine or bromine?
Chlorine.
Right. There you go. This is one of the problems from the homework. It looks like. And we have a bromine here. Chlorine axial, another H over here, fluorine going down, OH, an H going up, a CH3, a Cl axial or equatorial, fluorine equatorial, and a H axial. Okay. So it's a pretty complicated little molecule. But, alright, so let's start identifying some things. So they're going to ask us, Let's see, they're gonna ask us saying, so if I asked you guys, let's try to translate this to this maybe, backwards. Yeah. So I'm just gonna arbitrarily start numbering the carbons. Actually, I shouldn't arbitrarily do it because bromine would be number 1. But 2, 3, 4, 5, and 6. So it's at 1, 2, 3, 4, 5, and 6. So what's on carbon 1? Bromine. So we're gonna say bromine's going up or bromine coming out at us or away from us? Top of the ring or bottom of the ring? We'll say the top. Okay, and then what has to be going down then? The H's. Good. Carbon 2. We have a chlorine and a hydrogen. Is the chlorine cis or trans to the bromine? It's trans to it, right? See, it's on the opposite side of the ring. The bromine's on the top, the chlorine's on the bottom. So we say the chlorine is going dashed, while its hydrogen is wedged. Okay? Carbon 3. OH and H. Is OH cis or trans to the chlorine? Cis. Good. I'm just drawing one conformation. I didn't say this was the most stable energy conformation, right? Yeah, so this probably isn't, that's what we'll do after this. We'll do a ring flip and then we'll discuss. Okay? What's on carbon 4? Fluorine and an H. The fluorine is cis or trans to the OH on carbon 3? Trans. The fluorine is trans to the OH. So fluorine's going up, the OH is going down. There's H. Carbon 5. Fluorine and chlorine are what to each other? Chlorine on carbon 5 is cis or trans to the F on carbon 4? Trans, so it's going down. That means the CH3 is going up. Carbon 6, the chlorine and the fluorine. Carbon 6 is a fluorine and a chlorine. Nope, say it again.
Fluorine and hydrogen.
Fluorine and hydrogen, thank you. The fluorine and the chlorine are what to each other? Cis or trans?
Cis.
They're cis. So the fluorine's also on the bottom. Which means the hydrogen is on the top. Good. So let's try a ring flip now. And then we'll judge to see which conformation was lower in energy. It's not as good as drawing these ones. So what happens on a ring flip, right? Carbon 1 here, the head, right, got pulled down and became the footrest, and the footrest became the headrest. So let's number our carbons accordingly. 2, 3, 4 became the headrest. 5, 6. And even easier, if you don't even want to worry about this, you can start drawing the bonds in before anything else, right? Right, you can draw the bonds in that way. Right, so carbon 1 has what on it? Bromine, and is it pointing up or down?
Up.
So if it's pointing up, what position does it have to be on the new ring? Equatorial or axial? Good. There's the H. Carbon 2 had a chlorine and an H. Where's the chlorine now? Equatorial, axial? Equatorial. And this is axial. Carbon 3 had an OH and an H. Where's the OH at now? Axial or equatorial? Axial, good. Alright, it's on the bottom side of the ring. And now the H that was axial now is equatorial. Carbon 4 had a fluorine pointing up. So now on carbon 4 is it going to be axial or equatorial? Has to be axial, right? This fluorine was on the top face of the ring, right? It was pointing up. It's up. Right, if I marked all the ups, this is an up, 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 up. Down, 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 down. Right? So fluorine also had a H with it. Carbon 5 had what going down? A chlorine. So now the chlorine is going to be axial equatorial on carbon 5.
Gotta be equatorial.
If it was
Axial going down.
it was equatorial pointing down here. What side of the ring's going to have to be on now if it's going to be on this carbon 5? Has to be axial. This is down. That means this CH3 will be right here. Good. Okay. Oh, we didn't do carbon 6. Carbon 6 has a fluorine and an H. The fluorine was pointing down before. Now it's going to be axial or equatorial? Equatorial. Good. Okay. So now which of these two conformations, right? These are two conformations. No bond's been broken. This is the molecule moving. Which one do you think is going to be lower in energy? The top or the bottom one? Why the bottom?
Bromine and the Cl and equatorial.
Put a bromine in a Cl equatorial. Bromine's the biggest thing here, right? Of all the elements here, we have chlorines, fluorines, and bromines and OHs. Bromine's the biggest, so I guess maybe it'd be best to have the bromine, right? Have the bromine be equatorial. Maybe that makes this one the more stable conformation, but I don't know for sure. Because there's a lot of other stuff going on here. So the question they asked in the actual homework, though, was when the bromine is axial, what is the one thing it probably bumps? What are the two things it probably bumps into the most? So here's the bromine when it's axial. What does it bump into the most, do you think? The other axials. Which axials? Tell me which carbon they're on. Well, here's bromine. It's on the top.
3 and 5.
This hydrogen is also on the top. And this CH3 is also on the top. And they're axial with the bromine. So those are the ones that are most likely for it to interfere with, right? It has that eclipse, that bad interaction that makes it an unstable conformation, or less stable conformation.